Hi, welcome to the screencast for 9.2 on redox equations. So, as mentioned in 9.1, even though oxidation can't happen without reduction, we do often separate the redox reaction into the reduction and into the oxidation halves. So we call these half equations. And electrons are added to the more positive side of each half equation. So you list the species with its oxidation number before and after, either increasing or decreasing. And then you include the electrons on the more positive side of each half equation so that the charges are balanced with the other side. Because in chemistry, we don't subtract. We show the before and after. So, for example, you might remember a couple of these examples from the previous notes from 9.1. It says, decide which species is oxidized and which is reduced. Determine how many electrons are gained or lost per atom. So if I'm going to scroll down here a little bit, you'll remember with H2 and O2, those are both going to be 0 because they're elemental. Over here, H2 is going to be a +1. Oxygen is going to be a -2. So hydrogen is being oxidized. I'm right in the middle of my wrinkle here, so let me drop down a little bit. So hydrogen is oxidized, and each hydrogen is losing 1 electron, whereas oxygen is being reduced and each oxygen is gaining 2 electrons. On the second one, Ca goes from 0 to the +2, so I can tell that calcium is being oxidized, and in this case it is losing, make that work, it's losing 2 electrons. Tin, on the other hand, is going from +2 to 0 over here, so it's being reduced and it's losing 2. And the last one, hydrogen's a +1. It's still a +1 over here, so that's the one that's not involved, but that means nitrogen goes from a +3 here, oxygen is 0, oxygen's a -2 and a -2, whereas nitrogen's a +2. So nitrogen's going from a +3 to a +2. So it's being reduced and it is gaining an electron in the process. Oxygen is going from 0 to -2. Which I got this backwards here. Nitrogen is a -3 over here. I know I had something goofed up. Okay, sorry about that. So this is a -3 since that's a +3. So it's going from a -3 to a +2. So that's an increase in charge. It's being oxidized, and it's actually losing 5 electrons. Oxygen, on the other hand, is going from 0 to a -2. So oxygen's being reduced, and it's 2 electrons that it's gaining. Okay, hope I didn't screw you up too much on that. So then, as far as balancing them, the reason you would balance using oxidation reduction is sometimes inspection just won't get it balanced. So if you know the species involved in a redox reaction, you can balance the equation using the half reactions, and you balance each half reaction and then move on and combine them to balance the whole reaction. So the basic rules are you assign oxidation numbers to all the species, you write the half reactions using net ionic notation, you balance the half reactions by inspection, and just like before with minnow, you save the hydrogen and oxygen for last. Then you go ahead and balance each half reaction for charge by adding the electrons to the more positive side. Then you equalize the total number of electrons in each half reaction. So if one is losing 2 electrons, the other's gaining 4, you'd have to double the oxidation reaction where it's losing just 2. So you get the least common multiple so that you have the same number of electrons being gained and lost. And then you add the 2 half reactions and double check for a balanced equation. And then here's the goofy part. If the hydrogen and oxygen don't balance, you add water to the side needing oxygen, and then hydrogen ion to the side that needs it. Generally, it'll be the opposite side of where you added the water. So you might want to take a screenshot of this, but keeping all this in mind, we're going to go ahead and try a couple here on the next screen. Okay, so following our set of rules, I'm going to assign oxidation numbers. So magnesium is going to be 0, nitrogen 0. Magnesium has a preferred of +2, so that takes priority, which means the nitrogen is going to be -3. So now if I write my half reactions, my oxidation reaction, and you don't have to label them as each, but just so you know, is I've got Mg with no charge becoming 3, oh, this darn wrinkle, let me move down a little bit. So I've got Mg with no charge becoming 3 Mg ions, each with a 2+ charge. And then I have N2 is going to be reduced, and it becomes 2 N ions with a 3- charge each. And then I have to balance on each side, so I'll need a 3 here. I don't need a 2 there, it's already covered. I should have just had a N over here with a -3, and then I realize it's going to need, oh no, I'm sorry, it was already 2 in the equation, so I moved the subscript up. So now I want to go on and add the electrons that I need to each one. So the more positive side is here, and since I have 3 magnesium with a +2 charge, I need 6 electrons on this side. And if you're doing this right, now the other one will need the electrons on the opposite side, so they cancel out when I add up. And that is true. I need 6 electrons here to form the 2 nitrogen ions. And now I can go ahead and add this up, and I've got 3 Mg plus N2 plus 6 electrons yields 3 Mg ions plus the 2 nitrogen ions plus 6 electrons. So then my electrons cancel out, and I can see that this actually is forming the compound Mg3N2, and my equation is now balanced. And again, that would have been a pretty easy one to balance by inspection, but we're going to start out with easy ones so you can see what you're doing. So I'm going to go ahead and write in my solutions for the next 2 equations. I'd suggest that you pause and see if you can write in the solutions on your own before I walk you through them. Okay, so if I start again with assigning oxidation numbers, I've got Al at 0, Cl2 at 0, and over here, chlorine's going to have preference at a -1, and since there's 3 of them, that means aluminum is a +3. And again, these are working out just like we expect, and I know you could balance this by inspection, but humor me here. So I've got aluminum going from 0 to becoming an ion, Al +3. So that's balanced. I've got chlorine gas becoming 3 chlorine ions. So this one isn't balanced. So I'm going to need a 3 here, and I'm going to have to bump this up to 6 chlorine ions to balance. And now I can go ahead and add in my electrons. I would need 3 electrons on the positive side here to balance. And I'd need 6 electrons here to balance. And now this is where the next step comes in handy. Before I add these up, I have to come up with the least common multiple for electrons to make them balance. I've got 6 and 3, so this is going to have to be doubled to 2, 2, and 6 electrons. Now I can go ahead and add up. I've got 2Al plus 3Cl2 plus the 6 electrons gives me 2 aluminum ions plus 6 chlorine ions and the 6 electrons. So my electrons cross out. These are elemental forms of aluminum and chlorine. So over here, I just need to recombine these into the Al2Cl3, and that means I have 2 of them. I'm sorry, it's just AlCl3, and I have 2 of them. So I'm going to pause and move on to the final one. Okay, my final example, this one's not quite so clean, but I've got nitrogen. Okay, and our last example is a little messier because I've got a polyatomic ion involved. So I've got a -2 charge on my oxygen, It's going to have a total charge of -6. Overall, this ion has a -1 charge, so nitrogen is going to be a +5. Copper is 0. On this side, I've still got the -2 for a total -6, but now nitrogen's become a +6 and copper's become a +2. So if I look at my half reactions, I've got NO3 minus becoming NO3 neutral. I've got copper metal becoming copper 2+ ion. So I don't need to balance anything within these, but I do need to put my electrons in. So here I'm going to need 1 electron for the nitrate and 2 electrons for the copper. So then finding my least common multiple, I would need to double this to 2, 2, and 2. I can go ahead and add them up then, and I've got 2 NO3 minus plus Cu plus the 2 electrons becomes 2 NO3 plus Cu2 plus the 2 electrons, and the 2 electrons then cross out, leaving us with our balanced redox equation. Okay, on this one, I'm going to clear my work here and start this over again. So I've got SnS2 plus O2, and real quickly I'm going to fill in my oxidation charges here. Sulfur's going to have the preferred charge at -2, so tin's going to be +4. Oxygen's 0. Over here, oxygen's still -2, so tin is still +4. Still -2, sulfur's +4. So my half reactions, I'm going to have S2, and actually I should write that 2S because it's an ion. I've got 2S at -2 becoming just the 1S at +4, so I'm going to have to balance that with a 2 there. And then I've got O2, which is a molecule, so that can stay together, becoming, I've got 4 oxygen ions over here, each with a 2- charge. So I'm going to need to add a 2 here to balance that. And now as far as electrons, over here, -2 to +4 is actually 6 electrons, or 12 total. And over here, this is a gain of 8 electrons for those 4 oxygen. So now I'm going to have to increase both of these. I'm going to have to take this times 2 and this times 3 to get the least common multiple of 24. So when I do that, I'm going to end up with 4 S2 minus plus the 6 O2 and 24 electrons. On the other side, that's going to double to 4 S4 plus ions, the 24 electrons, and then 12 oxygen ions on this side. So when it's all said and done, the 24 electrons go away, and now we can look at bringing the SN back in. So if I have 4 S ions, that means I've made 2 molecules of SnS2. The 6O2 just remains as is. On the other side, the 4S, that would be 4 SO2 ions. And then that uses 8 of my electrons, leaving 4 more to form 2 SnO2. And if you look, we are balanced with the 2 tin on each side, the 4 sulfur on each side. And if we count up our total oxygen, I've got 12, and then 8 plus 4 is another 12. And now you might notice that this is actually a multiple of 2. So most people would go ahead and reduce this to 1, 3, 2, and 1. So let's look at a couple more examples if we have time. So this example is similar to the tin example we just tried. I'm going to pause it and do all my work since I have under a minute left here. And I'd suggest you try the same and then see if you can follow my work through. So go ahead and pause and try this one, and I'll put up my solution and then show it to you just briefly before we talk about the last slide. So check the solution over and see how the method works, even though it was an easy inspection problem. Moving on to oxidizing and reducing agents, remember these are opposites. If it's oxidized, it's considered a reducing agent, and vice versa. So looking at this equation, because oxygen's -2, you got Fe3 plus going to 0. So what is reduced? Fe3 plus. It's important that you include the 3 plus so you know it was an ion becoming the metal. And then what's oxidized? My carbon is going to be oxidized because it's going to go from 0 to a +2. And again, you would just say carbon there. So then the oxidizing agent is Fe3+, the